All right. In this video, what we're going to talk about is the electric field. What is an electric field? Like, what's the meaning of it? How do you interpret what an electric field is, and what we can calculate from it? So the point of an electric field, let's say we have a positive charge, right? If I have this positive charge and I take a negative charge and I bring it close to it, we know that that negative charge is going to get attracted to that positive charge, right? You know that opposite charges attract, and you know that if this was positive, it would push it away, it would repel. So the question is, how is this positive charge attracting that negative charge through seemingly empty space, right? So all the forces that we've talked about up until now, like physics 1 stuff, was all, if I have an object and I apply a force to it by touching it, I can make the object accelerate, right? But in this case, there's nothing touching, right? It's how does it exert a force through that empty space? So it's the same kind of idea as if I have the Earth, right? And we know the moon orbits around the Earth, unless you're a stupid flat earther, but we won't get into that. So the moon's orbiting around the Earth is, gravity is keeping the moon tethered to it. But how is that force, how is that force acting through what basically is empty space? Like, what's happening there? So a scientist in the 1800s named Michael Faraday did a lot of work with electricity and magnetism, but he came up with this idea of what's called a field. And he said basically that this positive charge, right, when you have something that's got a charge, it creates a field in space around it. And so that field looks something like this. So he said there's a field that this thing is making that's permeating out into space. And what you see as the force that this attracts with is really just this negative charge entering the positive charge field and interacting with it, right? And so if you have a charge enters the field of another one, those two interact and it creates the force. Same with Earth and the moon. So gravitational fields are an idea, right? So the Earth has a field pointing around it like this. And when something with mass comes into the Earth's field, it interacts with it and it feels an attractive force from gravity. And so if you remember, the reason the moon stays tethered around the Earth is the moon is moving, let's say, like this way, but it always has this tangential velocity component. So that velocity component is always going to be tangent to the field lines of the Earth, and so it moves around in a circle and doesn't really lose any energy as it goes around, and that's how it orbits, right? But the idea of a field is what's causing these things to seemingly interact at a distance. Okay, so some important things to remember about a field. The field is not the force. Force and field are two separate things. The field is created by the charge, and it exists everywhere in space around the charge, like theoretically out to infinity. That field goes everywhere. And what happens is when another charge enters that field, then a force is created, right? So the field is not the force. Remember, force needs two things to happen. So in this case, I can have a force from the positive charge on the negative charge because there's an A and a B. There's two objects there, right? There's no such thing as a force all by itself. You can't just have a random force without another object to act on. Forces have to come in pairs, right? Newton's third law. And then the other thing is that the field shows what happens to a positive charge when it enters the field. So the convention that we're going to use, because there's positive and negative charges, the convention is these lines will show what's going to happen to a positive charge. So I know if I put a positive charge right here, the field lines are pointing away. So that means that this is going to feel a force pushing out. And this negative charge, the field lines are pointing away, but because a negative is opposite, it's going to do the opposite of what the field line says. So this negative charge is going to feel a force pushing opposite of the field lines. Because again, the convention is for the positive charge. Okay, so what does the electric field tell us? Right, so first, it shows us the direction of the force on a positive test charge somewhere at some point in the field, right? The arrows show the direction. We can also get the strength of the field. The closer the field lines are together, the stronger the electric field is at that point. So let's say I have 2 points here. So here's point A, and here's point B, okay? Without the field lines there, you know from Coulomb's law, right? That the closer you are to this charge, the stronger that force is going to be, right? So you know that A is going to have a stronger force. If I put a charge at point A, there's going to be a stronger force than if I put the charge at point B, because A is closer and B is further, right? But you can get that from looking at this diagram without having to know what charge is there. I see at A, if I drew a little box, right? I have more field lines in the little box I drew at A than if I draw about the same size box at B, right? So imagine me drawing more lines out. There's more field lines here. There's a greater density of field lines at point A than there is at point B. So I can tell by looking at it that where the field lines are denser, there's going to be a stronger field. And if there's a stronger field, the force will be stronger on whatever charge I stick at point A or point B. It also tells us the force per unit charge at any of these points, right? So if I take a charge and I stick it at point A, the electric field tells us the force per unit charge at a point. And so the equation for that is electric field is force divided by charge. And the units for the electric field, it's measured in newtons per coulomb, right? So if I rearrange this, I can figure out, if I want to know what force is going to act at a charge I put in the field, if I rearrange this, I can say that force is equal to the electric field times the charge. That's powerful stuff. If I know the value of the field, I don't even need to know what this charge is. If I know the value of the field, let's say at point B, then I can take any charge I want and I can stick it at point B, and I can know the force that's going to act on that charge because I know the field, right? This is the electric field at that point. This is the charge that I'm going to stick here, and I can solve using rearranging this to get the force that that charge will feel. I don't even need to know this. It doesn't matter if I know what the field is. So how do I get the electric field? Okay, let's think about this. I know that electric field is force over charge. And I know that force from Coulomb's law is K times Q1 times Q2 over R squared. So all of that over Q. So if this is K, Q1, let's say, is the charge making the field, and Q2 is the charge that I'm going to stick in the field. Well, down here, I divide by that same charge that I'm going to stick in the field. So this cancels out. So to get the value of the electric field anywhere, right, if I want to know what the field is, cancel my Q, it's just K times Q over R squared. Right? These are our two basic formulas. So this formula is if I know the field and I want to know the force that is going to act on a charge that I stick in the field, right? I can rearrange it to get this. This formula is how do I find the field, right? So if I know what this charge is and I know how far away I want to measure the field, right? This distance would be R. This would be my Q. K is 9 times 10 to the 9th. I can solve for the value of the field there. So now, my toolbox, I can figure out the field, and I can figure out what to do with the field. This is really good stuff. You can solve for anything you stick in this field. Okay, so let's start with the charge. I know that I can pick any point around here because I know what the field of a single point charge is going to look like. This is going to have field lines pointing away from it. So I can pick a random point, like let's say right here. And I know that at this point, the electric field is going to point that way. Okay, and I'll call that, it's the electric field from the positive charge. What happens if I throw in multiple charges, right? Because you're not always just going to have one charge. So let's say I put a negative charge kind of right in the middle between these two. Positives, field lines go away. Negatives go towards. Because remember, the convention is what this does to a positive test charge. So a positive test charge will be repelled from a positive charge, but a positive test charge will be attracted to a negative. Okay, so let's draw the field that's going to happen because of this negative, right? So this negative charge at this point, it's going to attract a positive test charge towards it. Okay, and so you can kind of see where we're going with this. If you use superposition, right, I can say that the sum of what's happening at this point is the sum of the vector sum of the individual vectors I have here. So if I add these two vectors, you should be able to see that the net field at this point is going to point that way, right? And so I could do this at a bunch of different points. And as I start adding more and more of these points, what you get is a map of vectors that show up, okay? And so there's an easier way. I could draw every single point and then draw the vectors, but there's a way to draw field lines where you can get the same information from. And that would look kind of like this. So this is a set of field lines that show the electric field all around these two charges. And so you can kind of tell, here's the one where I did it by adding vectors. So see in the middle, the field points towards the negative. Up here, right, equal distance away, the field line points this way. Over here, the field line's kind of pointing up and away, right? Down at the bottom, it's pointing sideways. Back here on the back side of the negative charge, right? So this field map gives you the same thing as if you individually drew all the vectors around it, but it's more useful. So here's another one with two positive charges. And so looking at this field diagram, you can kind of tell that these two positive charges are going to repel each other. You can look at this one and you can tell that they attract each other. And so the way to interpret this, again, this is what happens if I put a positive charge anywhere in this field. So if I put a positive charge right here, I know that it's going to be pointing somewhere down here. So the way to interpret these lines is the field is always going to be at a tangent to these lines, right? So if I picked a point right here, right, the field at that point points at a tangent to this line. So right here, it would point there. Over here, it would point kind of like that. Right here, it would point kind of like that, right? You could do this anywhere. So right here, it would kind of be down. So the field lines, if you draw a tangent to those field lines, that shows you the direction of the field at that point. The other thing about this is field lines do not cross. Okay? Field lines cannot cross because if I had a point, let's just say, for example, I had a positive and a negative, right? And I said there was a point right here where, let's say my field lines did this, right? Instead of going like that, they crossed right there. There's no way that you can have two lines crossing because that means that at that point there's going to be two different forces coming from the same thing, right? It doesn't make any sense. These lines cannot cross because there can only be one vector sum force at any point in there, right? So field lines do not cross. There's a whole bunch of other examples of what field diagrams can look like. These are the two simplest cases for like positive charge and positive charge, or positive and negative, or if you had both of these negative, it would look similar except the field lines would be pointing towards, right? You can also have multiple charges and fields because of them, right? Something like these examples. So if you look at these examples, you can tell by looking at the field where it's stronger, where it's weaker, right? Because you can see the field lines are closer together or further apart. Even though there's multiple field lines in some of these, you can still tell where it's strong or weak. And then if you wanted to calculate how much the force would be at any point or the field, you could use one of the equations we showed, right? You could also have diagrams like this where you can see field lines, but you don't see any charges, right? But you should still be able to look at this and tell where the positives and negatives are and where the field is strongest. So if I look at this, there's no field lines in the middle, so I know it's going to be weak right here. And I know that these arrows are all pointing down this way. So if the arrows are pointing towards it, that must mean there's a negative charge here. And for the same reason, these arrows are pointing away, there must be a positive here. Here they're pointing towards, so it's a negative. Here they're pointing away, so it's a positive. So you can take charges and look at fields and see what's going to happen, but you can also interpret a field and figure out where the charges are. So in another video, I'm going to show you practice solving for electric fields, right? Actually numerically solving for it. But for now, you should be able to look at a set of field lines and interpret what's going on, where it's stronger, where it's weaker. And you should know those two equations for how to solve for the force in a field and how to solve for the value of the field.